looking at these notes, electric potential and conservation. So that guy you see on that picture, his name is Walter Lewin. He is a physics professor, or maybe was, I don't know, he's still teaching, at MIT, and he's doing the conservation of energy pendulum ball, the face thing there. All right, so sources of electric potential. So how is electric potential created, this voltage that we've talked about? So if electrons were transferred from the right side of a capacitor to the left side, if you physically took them off one side, put them on the other, you would give the left electrode a negative charge and the right electrode a positive charge. And the capacitor would have a total of no net charge, right? But the charge would be separated. And so a potential difference is typically created by separating positive charge from negative charge, because the charges are already there. So here you see we have an uncharged capacitor, and if you have this positive charge here, say a positive test charge, if it starts at point A and it gets moved to point B, there's no work required to go from point A to point B, right? Because there's no difference, because there's no charge, there's no field, there's nothing. It doesn't matter if it's at point A or point B, it's the same. But when we charge up our capacitor here, so we have negative on this side and positive on that side, you can apply force to this charge to move it in this direction, because it doesn't want to move closer to the positive charges, okay? So, because this charge here is repelled from the positive plate and attracted to the negative, the hand must do work, right? So in this case, there must be a potential difference, delta V, when you go from here to there. Does that make sense? So we know that there's a difference in potential. And you can think of it in terms of like gravitational potential. Like this is equivalent to just moving a box along the floor. Like the box doesn't care where it is, it's on the floor. So putting it, in the corner versus in the middle of the room, the box is where the box is. But if you're taking that box and moving it up, well, you have to do work to move it up, right, against gravity. Okay, so here we have some metal wires that are attached to the terminals of a 3-volt battery. What's the potential difference between points 1 and 2? Potential difference is also known as what? Voltage. So,
what do you need distance for it?
So here, this is just a 3-volt battery, and so what this is saying is the difference in voltage from the top electrode to the bottom one is 3 volts. And so, well, these wires are essentially, wires have resistance, as we'll see, but for most things, wires are pretty short, and we can ignore the resistance. Now, if you're running like power lines, like from your power plant to somebody's house, like those are going to have a significant resistance because of their length. But if you're talking about like wires and like a circuit, they pretty much don't have resistance because it's just such a small number. And since it basically has no resistance, it'll have the same voltage as, both ends of this wire will have the same voltage because there's nothing to use the voltage on the wire. So whatever these things are connected to, like this will be, the difference here will be the same as the difference here. Now, here's the deal with the voltage. It just says that the difference between the two ends of the batteries is 3 volts. It doesn't actually tell us what a particular voltage is. Because we always have to measure voltage in reference to something. So we know this potential difference here is 3 volts, because it says it, but like what I'm saying is the top could be 3 volts and the bottom could be 0. That's typically how we think of it. But literally it could be anything. Like the top could be 17 volts and the bottom could be 14 volts. But the difference is still 3 volts. And so, it could literally be anything. It just depends on how you build a battery and so forth. So, but once you know that this difference is 3 volts, well then, it would still be 3 volts over there. Okay. All right, so metal spheres 1 and 2 are connected by a metal wire. What quantities do they have in common? So the same potential, same electric field, same charge, both A and B, both A and C. So what's another word for potential? Voltage. And electric field is obviously E, and charge is Q, so. So I think. Well, how do we calculate electric fields? Q over R squared. If
They
it seems reasonable,
do they have the same field though? Is that one bigger?
one is bigger. Okay, well, let's think about this. So they're connected by a wire. We all agree with that?
Yes.
What did we say about the last question about that wire being connected to the battery? They all have the same voltage. Both ends of the wire will have the same voltage. So both ends of this wire should also have the same voltage. So they definitely have the same potential. Does that make sense? Because if they don't, what's going to happen is electrons will move until they are at the same potential. Okay, so as soon as you connect something with a wire, those two objects will have the same potential. Okay, so A is at least part of correct, right? So now we have to look at these other two.
So they don't have to have the same charge, because the potential is just, because earlier you saw like the battery could have 3 volts up here and 0 down there, right? So like they don't have to have the same charge?
They don't. So what's interesting here is if they had the exact same size, if 1 and 2 were the same surface area, then those things would be all the same. But because they're not the same size, when we connect it with a wire, what will happen is charges will move until they're at the same potential, right? So like V1 would equal V2. But V is KQ over R. And if you think of R as the radius of this, well, they definitely have different radiuses. And K is a constant. So if they have the same voltage with different radiuses, what also has to be different? The charge. Which one has more charge? They'll have the same surface amount of charge. Like the amount of charge per unit area would be the same on both, because that's determined by your voltage. But because this has more area, this would have more charge. And because this one has more charge, with the same radius, it would also have a stronger electric field. So, right, KQ over R squared. But I'd say the important thing to remember is you connect something with a wire, it'll have the same potential. And then whether or not they have the same charge really depends on the surface area. Same surface area, then they will have the exact same amount of charge. Because the way I like to think of it is like, imagine this instead of being 2 separate spheres connected by a wire, imagine it, when I connect it, I just make one larger sphere. And so all of the charge will equally separate over that surface, but kind of separate it like this. And so a lot of times when you see a question like this, they'll also say like, these 2 spheres are far enough away from each other that like this electric field isn't affecting this thing. Because yeah, if they're real close and they can start pushing on each other, blah, blah, blah. But we're not looking at all that crap. We're just trying to look at the stuff separated. Sources of electric potential. As you shuffle your feet across the carpet, you can cause a potential difference between your body and a nearby doorknob. Lightning is a result of charge separation that occurs in the clouds, and heavier particles fall to the bottom of the cloud and gain a negative charge. The negative charge at the bottom of the cloud causes a positive charge to accumulate on the ground below. A lightning strike occurs when the potential difference between the cloud and the ground becomes too large for the air to sustain. And so, I think I've said stuff about this before, I can't remember. But if you think here, like, this is our cloud, right? And so what ends up happening here is because of gravity, heavier things tend to be on the bottom. And what are clouds made out of? Water vapor. And water is what? H2O. And remember, oxygen likes to steal electrons. And so if oxygen picks up an extra electron, then that would naturally make that thing heavier than the other oxygen molecules around it. So those things tend to accumulate down here because of gravity, which means you could have a positive charge up on top. But that will induce, we already talked about induction, that will induce a positive charge in the ground, okay? And so then we'll get this very large vertical field, typically. Does this have to happen every time? No, you could totally have the opposite. But this is what happens, like, 75% of the time. And so what happens is if you get this voltage high enough, this potential difference high enough, air is a pretty good insulator, but again, you can overwhelm it. And so what typically happens with lightning bolts is they'll start, like these are ionized channels, and so it'll kind of ionize the air as it goes along and then make itself a nice little channel. Is that okay with that? I don't want to do too much detail, because I feel like we did that before. Sources of electric potential. A battery creates a fixed potential using a chemical process. Okay? All batteries use chemical reactions to create an internal charge separation. In biology, chemicals produce a potential difference of about 70 millivolts between the inside and outside of a cell, with the inside of the cell being more negative than the outside. The membrane potential of a cell is caused by an imbalance of the potassium and sodium ions. And so here, what typically happens, as it says right here, it says diffusion tends to equalize the concentrations of sodium and potassium inside and outside. But there's a sodium-potassium pump, and it uses your energy to force 3 sodiums out of the cell, but it only brings in 2 potassiums. And because they both have, a positive 1 charge, well, that creates your charge imbalance there. Diffusion ends up going the other way. So I'm not getting into too much detail here on the biology, but that's why it typically has, like cells typically have a 70 millivolt difference here between the inside and the outside of the cell. Yeah, and like I said, it's just caused by the difference in those 2 ions. Really. Okay, so if you're going to measure electric potential, you're going to use something like a voltmeter. And so this thing here is pretty much, this is a picture of a multitester, like we have multitesters in the lab. You'll notice that the voltmeter has 2 ends. And so whenever you test voltage, you're not really finding the voltage of that thing, you're finding the potential difference. Okay? Now, if we have something that we know to be 0 or neutral, then when you measure the potential difference, if this is actually 0, then you're actually can find the voltage at that point. Does that make sense? So the potential at a given point depends on where we choose V to be 0, but the difference is independent of any choices. And again, you can subtract the 2. The potential difference is measured for practical purposes, and we use a voltmeter. Voltmeters are nice and easy to use. You pretty much just turn them on and you just go, I want to measure voltage, and then plug the 2 leads in wherever you want to find the difference. So here is a micrograph of a nerve cell whose membrane potential is being measured. So like this is a nerve cell right here. There's another one down here. This is the micropipette that they have one of the voltmeter leads in. So here it says that you have a small glass pipette filled with conductive fluid is inserted into the cell's membrane. Second probe is immersed in the conducting fluid that surrounds the cell. So that's how they kind of measure some of these things. Is they have one just here in the fluid, and they have the other one essentially inserted inside the cell to measure the potential difference. And so you can get a positive difference or a negative difference, and unless you're really paying attention to what's going on, it's really just the location of your leads. So here's some definitions. We should know all of these things. So electric force, symbol F, electric field, symbol E. Electric potential energy, symbol U, the potential. And then we have electric potential, not energy, which is symbol is V. So here's your definitions and your units, right? Is this new stuff here? This should all be old, but just to reiterate, they can be a little confusing because they're all called electric something, first of all. I don't think you're confusing force and field too much, but electric potential energy are really easy to confuse. And so when you're reading these problems, just double check it. Oh, did it say energy? Make sure which one you read. Because again, field is going to be asked more than force, and potential is going to be asked way more than energy. But just be aware. So this chart here shows, well, everything that we've learned so far in electrostatics. So this side of the chart over here with field and force, these are vectors. These guys over here are scalars with electric potential and electric potential energy. And so you can see that this is a vector, right? Its force is K, Q1, Q2 over the distance squared. This is electric field. So we just lost a charge there. So to go from one to the other, F equals QE, right? And likewise over here with the scalars, we have U, K1, K, Q1, Q2 over the distance. And this is just K, Q over the distance. And again, U equals Q times V, or vice versa. The switch between these two. Since these are scalars on this side and these are vectors, it's real easy. You know, you just essentially multiply or divide by Q to change it. And remember that over here on the scalar side, you just plug all the numbers in and just take the answer. Over here, because these are vectors, they're going to have a direction. So you'll notice that the force and the field, the E has a little line above it to indicate that it's a vector. And so here, y'all might not be terribly familiar with this notation here. It's pronounced like N hat. It's got a little hat on it. And remember that Coulomb's law, for instance, K, Q1, Q2 over distance squared, this will only give you the magnitude, the size, but it doesn't give you the direction. And so I used a little thing called the unit vector notation to be like, okay, it has a direction and I put it over here, right? And so the direction just kind of depends on, you know, if we're just using positives and negatives for direction, then it would be over there separate. And so, again, do you plug positives and negatives in for like your charges here? No, you just want absolute value to find that. So just these little n hats, if you ever see that in a formula, I know when I first started seeing it, I don't think my teacher explained what was going on, but this is just the direction. And so it can look different depending on how you decide to express direction, or the problem decides to express it. And so you have to be careful when going from vectors to scalars or scalars to vectors, because technically these formulas, like the delta, you know, F equals delta U or delta D, like this should technically be derivatives, and this should be like a derivative to go this way and an integration to go that way. But we don't do that in this class, so you just see the deltas. And so essentially, you have to be very careful, especially going from scalar to vector, because this doesn't have any directional information on it. So you're going to have to think about it when you come over here. These don't happen too often. I'd say this one happens a little bit, but everything else here in the middle doesn't happen terribly often. But I wanted to give you guys this information, you know, especially if you go any further. I think it's a handy thing for electrostatics, because especially in like physics C and some of these more advanced classes, a lot of the problems you get in there will be like, okay, well, they'll give you this, like in the problem, and then ask you for this. And so you have to like somehow get over there. And as you can see, there's obviously more than one way to get there, or, you know, any of those things. And so it's just one of those things that, you know, it takes some practice or whatever. But I like this chart. I think it helps clarify, this is everything we've done in this unit so far. Does that make sense? So this is all electrostatics. So your first test, we just tested over this. notation of energy equation for a charged particle to be, kinetic plus potential equals kinetic plus potential. The total energy you have before should equal the total energy you have after, if energy is conserved. So if we have a charged particle, it could have kinetic energy, and it could have potential. In this case, we're just looking at electric potential energy. So if we want to switch out instead of energy, we could look at voltage. So we get kinetic plus, potential energy, but that's QV. Okay? So hopefully you guys can see these are basically the same equation.
Sorry, what was Q again?
Charge. So if you have the voltage, you just need the charge to find out. Electric potential energy. All right, any other questions right here? So, what we can do is we can rearrange that last equation. So this is final, and that's initial. So if I do final minus initial, like if I subtract the initial, I can get delta K. And likewise, I can get delta V. The Q will be the same Q, so we can just factor that out. So the motion of the charges can be written as the change in kinetic energy is equal to the negative times Q delta V. Because if you don't have the negative in there, then you don't have final minus initial, because initial minus final. So we want to keep our delta final minus initial. When delta K is positive, the particle speeds up as it moves from a higher to a lower potential. When delta K is negative, the particle slows down. Positive. Does that make sense? So this is actually pretty similar to our work energy theorem, which you guys should have learned last year. Work is equal to our change in kinetic energy. So here, like what are we talking about? So we have a positive charge speeds up as delta K. So here we have a 500 volt line, and so you can take 500, then 475, 450, 425, whatever. And its voltage is decreasing. You all see that? So you say our voltage change is negative 100 volts. You all see that? Going from 500 to 400. Well, if it's decreasing in its voltage, we have a negative QV. Right? So what's a negative times a negative? Positive. And this is a positive charge, right? So if we take 100 times whatever this charge is, that would give us a positive change in kinetic energy, right? And so here we can see like the little arrow representing the velocity as going up. Which makes sense if you think about like a ball rolling downhill. If this is like 500 feet, and the ball falls down to 400 feet, well, it's going to be going faster, right? And likewise, you would have the opposite if you did the opposite. Throw a ball up, it'll slow down. You're okay with that? Just things get a little weird because you have the negative charges as well. So a positive charge moves as shown. Its kinetic energy increases, remains constant, or decreases? It decreases. What? No, I just couldn't tell if y'all said increase or decrease. I just heard them at the same time, so. So it's going to increase your potential energy, but decrease your kinetic energy. Because the positive charge doesn't want to be over here, so if you throw it, it's going to slow down and probably stop before it gets to that point, right? So decrease your kinetic energy, but increase it.
Would you also have to account for the force of it, like when we go to the negative side?
Yeah. Well, that's why it's got both of them. Because it'll be pushed away from the positive and pulled towards the negative. So it wants to go the other way, which is why the speed's going to slow down. Proton released from rest at the dot. Afterwards, the proton stays there, moves up with a steady speed, moves up accelerating with an increasing speed, as it says. Moves downward with a steady speed or accelerates downward. The B or E?
E.
You can think of, these voltage things as essentially like, like your height in gravity. It's like, okay, this is at zero, but if it's zero, there's a hole below it, well, it's just gonna fall down, right? And it's gonna fall down, so it's gonna accelerate. Right? A positive charge is released from rest. It moves in the direction of a stronger field, a weaker field, higher voltage, lower voltage, or both B and D. Alright, well, hang on. Positive charge released from rest. Positive charge is released from rest.
Right.
What did it do in terms of voltage here? It went to the lower voltage. You know with me?
It's
So-
lower versus negative.
Huh?
It's lower.
Yeah.
Okay.
And so that's a lower electric, so it's definitely D. So the question is B true? Is it a weaker electric field?
I don't know.
Isn't it the same?
Is it? Yeah. It's typically the same electric field, because it's moving along the electric field line, so the electric field's probably gonna be the same. But it could increase or decrease depending on how the charge is shifted. Does that make sense? Like if you think about a parallel plate capacitor, well, the electric field wouldn't change.
Right.
Does that make sense? But if we just have like a charged sphere, and you put your other charge near it, well, then the electric field will get weaker as you go farther. So, and it could be stronger, but like that's two examples of it not doing definitely one or the other. But definitely in the direction of lower electric potential. So I think like ball rolls that way. So an electron will accelerate through a potential difference, delta V of 1 volt, gains kinetic energy. So delta K equals negative Q delta V. So what happens here is that the electron is negative, right? And this thing already has a negative, so now the E is positive here. Are you okay with that? E is positive. And then this is just a charge on an electron, 1.6 times 10 to the negative 19. Times 1 volt gives me 1.6 times 10 to the negative 19 joules. This is an electron volt, which already had an electron volt, because we went out of order. An electron volt is equivalent to, well, 1 electron times 1 volt spin. That's all it is. And again, it's more useful when we're talking about things like protons and electrons, because 1.6 times 10 to the negative 19 joules is not a very large number. But, we talk about like the ionization energy of like pulling an electron off of a thing. That would be, usually expressed in electron volts. So 1 electron volt is the kinetic energy gained by an electron, or proton, as it accelerates through a potential difference of 1 volt. So if an electron accelerated through a potential difference of 50 volts, well then it would gain 50 electron volts of energy. And then you can use this thing to convert it from electron volts to joules to be which you'd have to do if it asked for like the actual speed. Because you're going to be like, I got to go to joules, I can find the actual speed. Because electron volts has nothing to do with like meters. An electron starts from rest and is accelerated through a potential difference of 2 volts. What is its final speed? What direction will it move? And what would be different if it was a proton? So it says we have an electron starts from rest and is accelerated through a potential difference of 2 volts. What's its final speed? So first of all, what's its energy that it's going to get? 2 electron volts. Boom. There's a negative and a negative, it's a positive, so you have 2 electron volts. So that's how much kinetic energy it's going to gain. But we got to convert that to joules by using 1.6 times 10 to the negative 19. So we got that. So this thing here is 1.6 times 10 to the 19 times 2 volts. That will give us our change in kinetic energy, or our QV. Are we okay with that? And we know it started from rest, so our initial velocity is 0. Right, so we just have to calculate the final velocity as being 1/2. What the heck is this 9.11? here, I think that this is a pretty straightforward calculation. It's not a fun calculation, but you go, okay, I know how to do that. I don't want to. But it should be, you should look in your mind and go, yeah, I know how to do that. I don't want to do it, but I know how. Okay. So then the next question says, what direction will it move? Well, according to this picture, what direction will it move?
Down.
Down. So it will move from a lower potential to a higher potential, so down. And then if it was a proton, it would end up with the, not the same speed. It would end up with the same energy, but in the opposite direction. But would it go the same speed?
Goes slower,
Why would it go slow?
because it's bigger.
Yeah, 'cause it's bigger. So, that's wrong. Opposite. Did I have to fix something in last sentence? I can't remember now. Yeah, I think I put a C where there's supposed to be an F. But definitely not the same speed. The same energy. But again, it is significantly bigger than this, right? What's the mass of a proton? Still know that?
1.673 times 10 to the
Maybe
negative 27.
Yeah, so negative 27th is much different than negative 31st. So it's like 1,000 times bigger, so, actually, not 29. 10,000 times bigger? So, yeah, it would not have the same speed. So a proton has this speed when it's at a point where it's 100 volts. Then later, it's at a point where it's at a negative 150 volts. What's its speed later? So here, it's just running through the formula. We just talked about delta K equals negative Q delta V. Hopefully you guys can see a couple of things right here. First of all, it's going from positive voltage to negative voltage. So is it going to speed up or slow down? It's going to speed up, all right? So at this point, we can calculate the speed, but we know, okay, it's starting this fast, it's going to be going faster in a second. So then you just put it into the formula, and this is literally every step worked out. So, final kinetic energy minus initial, and so we have to solve for V squared. And then we plug in, negative Q delta V, so delta V is your final potential minus initial. So it's negative 150 minus 100 times the charge on a proton here. So we get all this stuff going on here. So here I went ahead and calculated the initial kinetic energy. And so we get negative the charge on a proton, final voltage minus initial. Just be careful here, because you're going to do negative 150 minus 100, which is negative 250. And then that negative, this negative will cancel, right? So then once you calculate this out, we get 4 times 10 to the 17th joules here. We got 1.02 times 10 to the negative 16th joules there. So then you can add that to the other side, right? And we get this, and then, just solve for V squared. Here, obviously, I took out the half at some point. Oh, no, it's multiplied it in. Okay, there we go. I hope I didn't lose that, yeah. Right, because half of this should do that. Okay, so theoretically that math is done right, but either way, y'all can check it on your own. If I did make a mistake, please let me know. So again, I feel like this is just one of those things, it's like, yeah, I can do that. You may not particularly want to, but I don't think that's terribly hard. But again, this should emphasize something to you. Like, I don't think any of these steps in here is difficult, but how easy is it to miss something?
Very easy.
Very easy. And that's one of the things that makes physics hard, is not so much like, I don't think this formula is hard, but like if I have to type, 1.67 e to the negative 27, if I just happen to forget this negative here, everything is destroyed now. So, one of the biggest things is you got to learn to, especially when you start these things, go slow. Go slow, make sure you get it right, and then the speed just comes over time. Because, it's like kicking a soccer ball at the goal. If you can't kick it, it doesn't matter how fast you do it. two protons, one after the other, are launched from point one with the same speed, right? So they both start right here, but they follow two different trajectories to show. Right? So they're launched at the same speed, but in different directions. Do they have the same velocity? No. The speed is the same. So obviously one is going straight up here, and the other one is fired essentially horizontal. Okay? They follow the two trajectories shown. The proton speeds at points 2 and 3 are related by 2 is faster, 3 is faster, or they're the same speed.
Is it
I got now, there's a couple of things here, and hopefully y'all encountered something like this last year. But first of all, it doesn't say velocity anywhere up here. No. That's important, okay? Because are they going to be going the same direction? Absolutely not. Okay. So, but remember, you can get your velocity from your speed. But if you're thinking in terms of components of your velocity, that will definitely throw you off here. Okay, like if you're thinking, okay, I have a vertical speed here, and I have a horizontal speed here, but this horizontal speed is essentially going to stay constant, but I'm going to add this vertical speed to it, right? But think of it like this. If I take a box, and I hold it up, and I just drop it, right? It has a potential energy because it's at the top, and as it falls, that turns into kinetic energy, right? So the top, it has 0 velocity, right? And it falls down, boom, it hits the floor, and depending on how far it falls, I can calculate that speed, right, based on conservation of energy. If I take a box, and the same box, from the same height, and I let it slide down a ramp, right? Which one will get to the ground first? The one I just dropped or the one that goes down the ramp? The one I dropped. Okay. Now, as this box slides down the ramp, there's probably going to be some friction slowing it down, right? But if we say that there is no friction, pretend like it doesn't exist, as it slides down the ramp, it's going to take longer to get to the bottom. But in the end, when it gets to the bottom, if there's no friction or anything to take my energy away, well, it started up here and it ended down there. So energy is still conserved. So it will take longer because it's going down a ramp, so it won't have the same acceleration. But because it took longer at a slower acceleration, it will end up with the same speed at the end. And so this is essentially what's happening here. This is going over a longer path, but it ends in the same location, right here, because it wants to fall down, so to speak. It wants to go away from positive towards the negative. And so here, if you're looking in terms of potential energy, it starts, at this height and ends at that height. So it will take a longer path, it will take a longer time to get here, but it will end up at the same speed. Again, not in the same direction, but it will end up at the same speed for the same reason the box sliding down the ramp without friction ends up at the same speed. Does that make sense? Everybody okay? No. There's a reason why there's so many problems that are like, oh, ignore friction. But that's just conservation of energy. And here, like the ramp, I can see, you're like, yeah, but in reality, it's going to have some friction. But here, there really is no friction. Or like a projectile flying through the air. It'll end at the same speed if I throw it to the side or if I throw it down. Just one will definitely take it faster. And that's where I think a lot of the confusion comes in, because like, the one going on this first path here, just straight up, is going to get there so much faster. And you're like, well, it went faster. Well, it accelerated more. So it got done faster, but they ended with the same speed. An electron follows the trajectory shown from point 1 to point 2. At point 2, so it starts with a velocity, let's call it v1 at point 1, and then the electron gets to point 2, ends with v2. Is that going to be the same as v1, bigger or smaller than v1? me ask you a question. Does the electron want to be close to that positive charge or far?
Close.
Wants to be close, right? It's attractive. So is it going to be going faster when it's closer or faster when it's further? Faster when it's closer because it's attractive. So which one's closer, one or two? One. V1 is bigger than V2. I don't know if this is helpful for y'all, but I also think whenever I see things like this, I think about like gravity and like planets orbiting. Like if this was the sun and this was the earth, first of all, y'all know that planets don't orbit the sun in a circle, right? They're close, they kind of look like a circle from a certain perspective. But when the earth is closer to the sun, it moves faster, and it gets slower as it moves further away. And so that just happens naturally in its orbit. And so here, I'm looking at this, and this to me just looks like part of an orbit. I'm like, well, it's closer there, it's further there. It's going to be faster here, slower there. Does that make sense? Because as it gets further away, this thing is going to pull on it and essentially slow it down because it wants it to come back. Make sense? At the end? That looks like the end. So that was a bunch of example problems there. So y'all still have 30 minutes left.